Today we will use vectors in our study of three-dimensional geometry. Lines and planes are the basic tools from which everything will be built off of. So in today's video, we would take the opportunity to learn as well as review the equation of a line and a plane. There are a few different forms for the equations, so we will learn the different forms and also learn how to convert in between them. Subsequently, in part 2 of this video, we will tackle the ASRJC 2019 prelim question, making use of what we learned here. We start with the line. So to form an equation of a line, we need two things. We need first a point, let's call it point A with position vector A. We also need a direction vector D that is parallel to the line. This is seen in this picture over here. So we will form the vector equation of the line as follows. L, that's the name of the line, is given by R, I'll come back to R in a while, is equals to A plus lambda D, where lambda is a constant. So let's see how this equation works. So for example, if lambda is 1, we have the equation R equals to A plus D. So A is over here, then we travel along the vector D downwards, and we end up at this point somewhere over here. So if lambda equals 2, however, then we'll travel a bit further down and end up a point further down. If lambda equals 1.5, we may end up with something in the middle, 0.5 somewhere over here, negative numbers traveling backwards, etc. So by varying the values of lambda, we are able to get the position vector of different points on the line. So that is what R is trying to capture. So we call R the general position vector of the line. Varying different values of lambda will be able to give us all the position vectors of all the points on the line. So let's take a look at the example with some numbers. So first we have this example. We are given the coordinates of a point A, which is 1, 2, minus 3. And also we are given the direction vector that the line is parallel to. So we have the vector 2, minus 1, 4. So to form the equation of our line, we simply need to write L is given by R equals to our point, 1, 2, minus 3, plus lambda of the direction vector 2, minus 1, 4. So pretty simple, right? So let's take a look at a slightly tougher example. So in this next example, we are given 2 points instead. We are not given the direction vector directly. So what we have is a point A, 2, 1, 4, and a point B, 1, 1, 7. So we need the direction vector to be able to form the vector equation of our line. So the direction vector for this case can be AB. So we use AB is equals to OB minus OA. So taking 1, 1, 7 minus 2, 1, 4 gives us the direction vector minus 1, 0, 3. So to form the equation of line AB, we have R equals to a point. We can use any point. So we can use this point A, we can use this point B, or any other point. So we decided to go with point A here. So R equals to 2, 1, 4 plus lambda of the direction vector minus 1, 0, 3. So take note that the point and the direction vector is a bit different in our vector equation of the line. So in forming the equation of a line, this is the vector form, the form that we have just learned. In fact, this is our preferred form of an equation of a line because it gives us two very important pieces of information. It gives us information about a point on the line as well as the direction vector. These are quite easy to visualize and will be very useful in helping us solve further questions down the road. However, we also need to learn a few different forms of the equation of a line. In particular, the second form that we will learn today is the Cartesian form. So in the Cartesian form, we will be rewriting our equation in terms of our usual coordinate geometry variables x, y, and z. So our final form will look something like this with x, y, and z inside. So we'll first learn how to convert from our vector form, as shown over here, into the Cartesian form. So our vector form, and as an example, we have R equals to 1, 2, minus 3, that's the point, plus lambda of 2, minus 1, 4, our direction vector. So how do we bring x, y, z into our equation? That's actually hidden inside R. So we let R be x, y, z, and we combine these two vectors to become this vector, 1 plus 2 lambda, 2 minus lambda, and minus 3 plus 4 lambda. We can equate each of the rows to get three equations. The first row, we have x equals to 1 plus 2 lambda. The second row, y equals to 2 minus lambda, and the third row, z equals to minus 3 plus 4 lambda. Each of the equation, we can also make lambda the subject. So from the first one, lambda is x minus 1 over 2. From the second one, lambda is y minus 2 over minus 1. And from the third equation, we have lambda equals to z plus 3 over 4. All these three expressions are lambda, so we can equate all of them, giving us this final equation, x minus 1 over 2 equals to y minus 2 over minus 1 equals to z plus 3 over 4. And we call this the Cartesian form of the equation of a line. To reverse the process, if we are asked to convert a Cartesian form back into a vector form, we will just reverse all our steps. Let each of the parts be equal to lambda, make x, y, and z the subject, join them up into R, and break up based on the direction vector as well as the point. There's also a shortcut. With more practice, maybe you're able to spot it. So if you take a look at the numerator, we have x minus 1, y minus 2, and z plus 3. That corresponds with the point, the position vector of the point, 1, 2, and minus 3. The denominator over here, 2, minus 1, and 4, corresponds with the direction vector. Sometimes we may have trouble carrying out the procedure we have outlined over here. So in particular, if there is a 0 in our direction vector. So let's have a look at this second example. So we will do the same as what we have done just now. We combine these two vectors to form 2 minus lambda, 1 and 4 plus 3 lambda, and we let R be x, y, and z. And we form our three equations. We have x equals 2 minus lambda, y equals 1, and z equals 4 plus 3 lambda. So the different thing here is that in our middle equation, there's no lambda, so we can't make lambda the subject. So we have to take this and put it on the side. We'll proceed with the regular procedure for x and z. So making lambda the subject, we have x minus 2 over minus 1, and lambda equals to z minus 4 equals 3. And since both are lambda, we can equate them and put a comma, y equals 1, because there's no lambda on this side. So if we want to convert backwards from the Cartesian form back into the vector form, we will follow the same procedures as well. Having some guy off to the side means that the corresponding component for the direction vector would be 0. So that wraps up our discussion on lines, the two forms, our vector form, which we prefer, as well as the Cartesian form. Now we will go on to planes. So a plane, it's an object, as seen over here, a two-dimensional object. To form a vector equation of a plane, we will need a position vector of a point on the plane, as well as two direction vectors. So it behaves very similarly to our vector form of a line. So in the line, we need a point and one direction vector. In the plane, we need one more direction vector. So the direction vectors are any vectors that are parallel to the plane, of which there are many inside the plane. So to form the equation, the vector equation of a plane, we take R, just like a line, equals to the point A plus lambda d1, and for a plane, we add another direction vector, plus mu, another constant, of d2. So it's just a slight extension to what we learned in lines. So let's take a look at the example. So in this example, we have a point A, 1, 2, minus 3, and two direction vectors, one of them being minus 2, 3, 1, and the other one I plus 2k, which is the same as 1, 0, minus 2. So to form the vector equation of this plane, we have the plane P is given by R is equals to the point 1, 2, minus 3, plus lambda minus 2, 3, 1, plus mu 1, 0, 2. So these two are our direction vectors. Unfortunately, unlike the line where the vector form is pretty clear-cut, we don't really like the vector form of our plane. This is because there are many direction vectors hidden inside a plane. So there are so many of them such that we will end up with a lot of different equations that may end up describing the same plane. So that's not very ideal. So when we handle a plane, instead of direction vectors, we actually prefer this thing called the normal vector. So a vector that is perpendicular to the plane. So up to a scalar multiple, this normal is actually unique for each plane that we are talking about. So this brings us to our second form of a plane, the scalar product form. So to make a plane in scalar product form, so to find the equation, we need two things. We need the normal vector as well as a point on the plane. So we have the equation r dot n equals to k, where k equals to a dot n. So this equation can be a bit weird, so I'll probably link to a blog post in the description below to explain how this equation comes about. Because the normal vector is so important to a plane, we'll be using this form very often. So with practice, hopefully we'll get familiar with this form of equation of a plane. So let's take a look at the example. So for the more simple example, we have a point A, 1, 2, minus 3, and the normal vector of the plane is given to us, the vector that is perpendicular to the plane, 6, 5, minus 3. So to form the equation of the plane, we need to find the constant k, which is given by a dot n. So we take the point, 1, 2, minus 3, dot the normal vector, 6, 5, minus 3. So the dot product gives us 6 plus 10 plus 9, which is 25. So we plug into our equation of a plane seen over here. So we have r dot the normal vector, 6, 5, minus 3, equals to 25. So since we like the scalar product form more because it tells us information about the unique normal vector, if we are given an equation in vector form of a plane, we probably would like to convert it to scalar product form. So how do we do this conversion? So the key idea is to observe that the normal vector is perpendicular to both direction vectors. So we can use the cross product to help us get the normal vector. So for this example plane over here, to find the normal vector, we will take the two direction vectors and cross them. So taking the cross product of these two direction vectors, 0 minus 6 giving us 6, and etc. It will give us a normal vector of 6, 3, and 3. So we can use this as our normal vector, but for simplicity, I spotted the constant common factor of 3. So I'll take it out, leaving us with 2, 1, 1, and I will proceed with this question by using 2, 1, 1 as the normal vector. So to form the scalar product form of the plane, we take a dot n. So a is a point, we have 1, 2, minus 3, dot our normal vector, 2, 1, 1, it will give us 1. So we'll write out the equation of the plane, which will be r dot our normal vector, 2, 1, 1, will be equals to 1. So other than the scalar product form and the vector form, we also have a third form, the Cartesian form, just like in our lines where x, y, and z will be involved. Thankfully, the Cartesian form is not very different from the scalar product form that we prefer. So we want x, y, z to come out and it will be inside R. So we let R be x, y, z and do the dot product, giving us x plus 2y minus 3z in this example over here. So x plus 2y minus 3z equals 6, and this is the Cartesian form of our plane. So the Cartesian equation will be very similar to our scalar product form. So to convert forward and backward is quite straightforward. The coefficients of x, y, and z, 1, 2, minus 3, corresponds with the normal vector, and the constant 6 are both on the right hand side. So the scalar product form as well as the Cartesian form is very useful because it allows us to visualize the normal vector. So from here, from these two forms, we can see that the normal vector is 1, 2, minus 3. Very often, however, we also would like to know the coordinates of a point on the plane. So unlike the vector form, which explicitly tells us that 1, 2, minus 3 is on the plane, if you are given a Cartesian equation over here, as well as the scalar product form, it may not be so clear what a point on this plane will be. So the trick is to actually just do inspection and do a bit of trial and error, sub in 3 numbers such that after the dot product, we will get the constant over here, this number 6. So there are many answers, and one trick is to just use a lot of zeros. So for example, if y and z happen to be 0, the next will have to be 6 for this equation to work out. So that means that the point 6, 0, 0 will actually lie on the plane because it satisfies the equation. There are many other possible answers as well. For example, 0, 3, 0 will satisfy the equation as well, and it will lie inside the plane. And I'm sure you'll be able to come up with many other points that will work as well. Usually we just need one. We will use what we have just learned to tackle some exam questions. In particular, the ASRJC 2019 H2 Math Prelim Paper 1 question 9. So the question goes as follows, and it has this diagram drawn for us. So the diagram above shows an object with O at the center of its rectangular base ABCD. So AB is equals to 8 cm and BC is equals to 4 cm. The top side of the object, EFGH, is a square with sides 2 cm long and is parallel to the base. The center of the top side is vertically above O and at the height h cm. So let us put all these dimensions into our diagram. So we have this diagram over here. So we have filled in, we have a square with sides 2 cm. So this side will be 8 cm for our rectangle below, and this side will be 4 cm, and the height is h. So for the first part of the question, we are asked to show that the equation of the line BG may be expressed as this below over here. So we have just discussed about how to find equations of a line. We need two things. We need a point on the line as well as the direction vector. But if the direction vector is a bit confusing over here, let's just focus on finding the position vectors of the points on this line first. So we are given the line BG, so let us find the position vectors OB as well as OG. To do that, we will use our picture. So we will start from O and we try to travel towards B along the 3 axes, along the I, J, and K component vectors. So to travel from O to B, as marked out over here, we will first travel half of this distance. So half of 8 is 4 units along the I direction, and then half of this distance, 2 units in the opposite direction of J. So this gives us the vector OB is equals to 4 along I and minus 2 along J. Next, we want to get OG. So we travel from the O upwards, which is h units, so h in the k direction, followed by half of this, 1 unit in the x direction, on the I direction, and minus 1 unit in the j direction. After we get OB and OG, we can then form the equation of our line BG. First, we need the direction vector. Direction vector can be given by BG, which is OG minus OB. So this minus this gives us minus 3, 1h. So the equation of a line, R, will be equals to a point. So we'll use OB as our point, 4 minus 2, 0, plus lambda, or t, of our direction vector, minus 3, 1h. So we don't need to use our constant to always be lambda, we can be t as well. And this answers part 1 of the question. So for part 2, we are asked to find the sine of the angle between the line BG and the rectangular base ABCD in terms of H. So we already have the equation of the line BG, and as we have earlier discussed, when we are talking about ABCD, which is a plane, the normal vector will often be the most useful. So if we observe in this picture, the vector k is actually the normal vector to the horizontal base ABCD. So we have our direction vector of our line that we have found earlier, minus 3, 1h, and then we have our normal vector of our plane, which is 0, 0, 1. So we have this formula that gives us the angle between a line and the plane. I'll discuss this formula in a subsequent video. I will link it in the description below after I've recorded it and uploaded it. So, but for now, let's assume we know this formula and let's just plug in what we have. So d is given, the direction vector is given by minus 3, 1h, the normal vector given by 0, 0, 1. To find sine of theta, we divide the magnitude of d and magnitude of n. To our simplification with our formulas to get the final answer, h over square root of 10 plus h squared. And this answer is part 2. For part 3 of the question, we are given that now h equals to 6. So let's update our picture. Instead of h, we'll now write 6 over here. We are now asked for the Cartesian equation of the plane BCFG. So at first this looks a bit intimidating. BCFG is this slanted plane over here, but to tackle questions usually, let's just try to think a bit more simply. Before tackling the plane, let's just find the position vectors of points on this plane instead. So we will probably like the position vectors of B, C, F, or G. In fact, just 3 is enough. We have already found the position vectors of B and G in our earlier part of the video in question part 1 when we find the line equation of the line BG. So we already have OB and OG. So we want to find a third one, maybe we find C. Okay, so we'll use the same procedure. Start from O, we travel 4 units along I, that gives us 4, and 2 units forward along J. So OC is given by 4, 2, 0. Given the points, the position vector of the point, we can then combine them to find the direction vectors. So combining OB and OG gives us the direction vector BG of our plane. So BG is given by OG minus OB. Similarly, we can also find BC given taking OC minus OB. So 4 minus 4 is 0, and 2 minus minus 2 is 4. So I'll simplify by taking out the common factor 4. Okay, so minus 3, 1, 6, and 0, 1, 0 will be the direction vectors of this plane that we are trying to find. To find the normal vector, which is the most important vector for all planes, we use the cross product. So we take our direction vector, minus 3, 1, 6, cross with 0, 1, 6. So working out the cross product and taking out the common factor gives us the normal vector of 2, 0, 1. Let's recall our equation of a plane is given by r dot n equals to a dot n. So a, we need a point, so we'll be using point C, 4, 2, 0. We can also use the other 2 points and we should get the exact same answer. So we take the point a dot n, dot our normal vector 2, 0, 1, the dot product gives us 8. This gives us the scalar product form of our plane. So r dot n, r dot 2, 0, 1 is equals to 8. The question, however, wants the Cartesian form, but that is pretty simple to get from here. By letting r be x, y, and z, we get our Cartesian form, 2x plus z equals to 8. And the answer is part 3. Finally, we are asked for the shortest distance for part 4 of the question from the point A to the plane BCFG. So we have just found the equation of BCFG earlier on. In particular, the most important vector is going to be the normal vector 2, 0, 1 over here. So to proceed with this question, we should probably focus on what's the position vector of A. We don't actually need to look at this picture with this weird slanted plane over here and the point A over here. We'll just use this picture to find the position vector of A. So OA is given by negative 4 units backwards of the I direction and negative 2 units backwards in the J direction. So this is OA. And we'll redraw a picture. We don't need to look at our plane, this slanted plane this way. We can draw a new picture where we visualize BCFG as a horizontal plane below. This can be done like by tilting our head, for example. So we have a point A that we draw above the plane. So the question asks for the shortest distance from A to the plane, which is this distance in red shown over here. So let's find the vector AC. So AC is given by OC minus OA. So we subtract the 2 position vectors to get this vector 8, 4, 0. We want the projection of this vector AC onto the normal vector. So as I've discussed earlier in the video, the normal vector will be very important in all plane questions that we'll be tackling. So our equation of plane is given by this. So we have our normal vector 2, 0, 1. So to find the projection, our projection formula is AC dot n hat. So we take AC dot our normal vector 201 divided by its magnitude. This gives us our final answer, 16 root 5 over 5. And that answers this ASRJC 2019 prelim question.